Hi! We're on daily lessons 171 to 173. Hooray! You didn't know what I was going to say. Did you think I was going to say like whoop whoop or let's do this thing? Any of those things could have gone that place, but hooray also works. Okay, so I know that you're seeing this and you're like, there's a lot of writing right there. We'll get through it together. I wrote it already so that I wouldn't put my hands over it at the same time. So the fundamental theorem of calculus, part 1 and 2. That is a big name. Fundamental theorem of calculus, that means it's going to be really, really important. Sometimes you'll hear this as FTC. You don't actually have to distinguish between parts 1 and 2, like they're used interchangeably because some books, part 1 and part 2 and vice versa. But here are both of them. This is what we're going to go with in this class. But if you just say fundamental theorem of calculus or FTC, that's good enough. So in here, if f is a continuous function, so that's good, we're talking about continuous functions, and a is a number in the domain of f, so if we've got an a over here, that's where you see this on this integral, then we define the function g by g of x is equal to this integral. So what this is, g of x is defined as an integral of f of t dt. So from a to some other value of x. So just some number, some x value to some other x value, but this x is any x value. Then g prime of x. So let's think about what an integral is. If I have a function and I take the derivative, I get the slope, right? But if you're given the slope, you go back to the original function. Well here, if g of x is the integral, so it's not the derivative, but it's like the function before that, it's whatever I took the derivative of. If I take the derivative of this, so, if I take g prime, I get the thing on the inside. And the only thing that you're going to see that's different for right now is that f, instead of it being f of t, it becomes f of x. So whatever that top integral or top variable is, which is usually x. So if I take the derivative of an integral, I get the stuff on the inside. They cancel each other out. Excuse me. Or if I take the derivative of an integral this way, and this one's more, this one's an definite integral, it starts at a place, it ends at a place. This one would be an indefinite integral, it's not from a place to another place. If I take the derivative of this integral, everything goes away and I'm just left with f of x. The other part of this fundamental theorem of calculus is if f is continuous and f is the antiderivative of f, then this integral, and we're going to talk about this more, from a to b, and we've got this derivative here of f of t, this integral is equal to f of b minus f of a. Whew, and this is capital F of b minus capital F of a when you're writing this. And you might be thinking, I have no idea what you're talking about yet. That's okay, we're going to get into it and then hopefully you will. So in here it says consider this function f of x. So what's given to me is this function, and you can see negative 2x plus 3, I start at 3, I go down to right 1, so this function is f of x, so is this one, and anything, it's because it's given, whose graph is pictured below. Calculate each of the following definite integrals. So a definite integral starts in like a definite integral will start at one x value and end at another x value. So this one will go from negative 2 to 1. So on a graph, it would go from negative 2 to positive 1. And I'm actually going to go backwards from what we just said that we were going to do. It says, then shade the area of the region of the integral represents. I'm going to do that first. So if I'm talking about the area under the curve, what I mean is the area between the curve and the x-axis. In this case, this curve is actually a straight line, so the function, the x-axis. So from here to here, this is going to be the base of my area, and if I fill in the whole way from negative 2 to positive 1, if I were to find the area of this region, so all that's right here, this is a shape I actually know. This is a trapezoid. Or you could break it into different shapes like some rectangles, some parts, and triangles, but that'd be harder. So this is a trapezoid. It's not quite just one big triangle down here. So to find the area of that trapezoid, I'd have to do 1/2 base 1 plus base 2 times the height. The height is the easier one to find in this because it's the distance between my x values. So this would be a distance of 1, 2, 3. Base 1 and base 2 are going to be the function value at -2, which we have this over here too if we want to see. I'm hoping it's just 7, but just in case it looks close. -2 times -2 is 4, plus 3 is 7. The function value at 1, -2 plus 3 is 1. Yeah, it's right here. So this area is something that I know. 1/2 times 8 would be 4, times 3 is 12. So I could actually find the area. And here's where I'm going to try to convince you. So what this fundamental theorem of calculus is saying, and I'm going to go with part 2 first, is that if I integrate this, what this really means is that I just get capital F of B minus capital F of A. That is the antiderivative. It says F is an antiderivative. So I don't have to worry about the plus C at the end. Because really if I do F of B minus F of A, and let's say I had a constant of 3, 3 minus 3 would still be 0. So if you're like, I don't know what you're talking about, it's okay. But F is an antiderivative, just one of them. May or may not have a constant at the end. If I do F of B minus F of A, I should get the same answer, the area under the curve. So let's try this. The antiderivative here would be x. I add 1 to my exponent. It started with an exponent of 1. My new exponent would be 2. So I add 1 to the exponent. I divide my coefficient of -2 by my new exponent. And just to be sure, take the derivative of this. I get -2x. Okay, I'm good. The antiderivative of any constant would be that. You just replace that as coefficient times x. And if I take the derivative of 3x, you would just get 3. And for this one, I do not need to put a plus c. Because remember what I'm leaning towards is F of B minus F of A. So let's say I put a plus 7. I would end up with a plus 7 minus 7, so it goes away. You don't need it. This is just an antiderivative. Good. And I'm going to evaluate this from -2 to +1. These are called my limits of integration. If I take f of 1 minus f of -2, so whatever the top is minus the bottom, if I substitute in 1, this would be 1 squared, and then I'm going to attach the negative onto that. So I would have, this would be -1 plus 3 times 1. 3 times 1 would be 3. Actually, what am I doing? I should do, this would be like -1 squared. It's weird because if you would put this in the calculator, but this is like -x, the whole thing squared. So this would be, okay, let's go back. Whew. So if I've got this -x squared plus 3x, if I substitute in 1, remember the order of operations is kind of weird, but this is like -1 times this quantity x squared. So I'm actually going to square this x first. I get 1 squared is 1. This becomes a -1. There we go. 3 times 1 would be 3. Minus f of -2. If I substitute in -2, I do the same thing. So -2 squared is 4. Attach this negative to it. 3 times -2 is -6. I would get 2 minus -4 minus -6 would be -10. What? I get 12. So even this way, I still get 12. That's very exciting. So if I'm finding this using the fundamental theorem of calculus, I still got the area under the curve. Hold on, not convinced. Let's do another one. Okay, this one's same function, but this time I'm going from 2 to 5. I think one of the hardest parts of this is just drawing it. So from 2 to 5, I'm going to make a horizontal line here. I'm going to go down until I touch my graph right there. I couldn't go up because I'm not going to touch the function. Same thing at 5. Okay. Funny, this area looks a lot like this one, but it looks like it's below the x-axis now. Let's try. Okay, if I see that this is a trapezoid still, 1/2 base 1 plus base 2 times the height. The height in this is going to be a distance of 1, 2, 3. Interesting, kind of looks like above still. This is all shaded, by the way. If I do this base, I could do right here, which would be f of 2. If you put it in here, that would be okay also. That'd be negative 2 times 2 would be negative 4 plus 3. Oh, sorry, what did I do? Negative 2 times 2 would be negative 4 plus 3, which would be a negative 1. If I go over to 5 and found f of 5 is negative 7. Hey, it looks like up here, except these are negative. Negative 4 times 3 is negative 12. This is below the x-axis. This one was above the same area. Any area that's shaded under the x-axis will be negative. Okay, so let's just see, does fundamental theorem of calculus still help us here? Could we take the antiderivative, so whatever this is, the antiderivative of that, which we found it in the last one, but it's good practice to go through that process of add 1 to the exponent, divide by your new coefficient. Here, the 3x, the antiderivative of 3 would become 3x. And I'm going to evaluate this from 2 to 5, meaning I'm going to take my f of 5 minus f of 2. Be careful, make sure you've got positive, or not positive, capital letters in there, f of 5, because we've got lowercase f of x is the derivative over here. If you substitute in 5, you should get 5 squared would be 25. Negative 25 plus 15 would be negative 10. This would be 4, negative 4. Negative 4 plus 6 would be positive 2. Yeah, negative 10 minus 2. FTC for the win. Okay. Anytime I hear the FTK, you know, like the Penn State, what they do for the thon, that's what I always think of. I think of FTC for the children, but fundamental theorem of calculus. Okay, let's do another one. So this one changes slightly because there's going to be some area above the x-axis and some below. So I've got negative 1 to 4. I'm still going to make this horizontal line. But when I start in this negative 1, I think I can't go down because I can't get to the function, but I can go up until I get to the function. At the other endpoint, the 4, I can't go up anymore because I can't get to a function, but I can go down. And then I can see the area enclosed would be this business. Do you notice anything about those areas? This area up here is going to end up canceling out with this area down there because they're going to be exactly the same. So the area between the curve is going to be 0. And if you want to actually do this on the side, and you're going to be like 1/2 base times height, and then at the bottom you do plus 1/2 base, but this height is -5 instead. This is how you do it. This is the area of the top triangle, this is the area of the bottom of the triangle. Area of a triangle is just area is equal to base time 1/2 base times height. That's how we get 0 for the area. Let's do a fundamental theorem of calculus. You try. What do I do to this? Okay. Did you take the antiderivative from -1 to 4? You get capital F of 4 minus capital F of -1. Substitute in. And you got -4 minus -4 or plus +4. Remember, this is substituting 4 into both parts, -1 in both parts. Common error on this is multiplying the negative before squaring. And then the other common problem on this is just putting like 4 in here and -1 in here. Don't do that. It has to be the whole function. Okay, let's do another one. This one, try drawing it. -1 to 3. On the left, I'm going to go until I hit my function. There it is. On the right, do the same thing. And I can see the area that's trapped in there. It's right there. That whole region. Same thing up here. Is this area going to be positive or negative? Or I could say, is the value of this integral going to be positive or negative? Positive, because there is more area above the x-axis than below it. Let's do it, if I were to find the area of this, I'm just going to do it on the side. And you can do it too. So 1/2 base, this is 2.5, a length of 2.5, the height of 5 over here. I put minus just because I knew it was below the x-axis. If you would have put plus here and then minus for here because the height is the thing that's negative, you could do that, but you could also just subtract the stuff below the x-axis. Take the antiderivative. By the way, check and see what you got done here. You should get 4. Up here, we're evaluating from -1 to 3. Remember, it's always f of b minus f of a. So you take whatever the antiderivative is. And this b, I should have filled that in. 3, -1. Okay, you try. This would have been -9 plus 9, so I get 0. If I substitute in -1, -1 squared would be 1, -1, minus 3 would be -4. Okay, another one. You try drawing this one from 0 to 5. Did you make a horizontal line? Go up to the function on the left, go down to the function on the right. It's this whole region. Will this answer with this area under the curve, or the answer to this integral, and this is always with whatever this function is, that's always the one that's graphed. You should make sure you notice that these are always the same function that's graphed. The stuff on the inside of the integral is the same as the area under the curve. Is this going to be positive or negative? Negative. Why? Because it's the area under the x-axis is greater than the area above the x-axis. So they're a triangle above, a triangle below. If I do 1/2 base times height, the base of that top triangle is 1/2, the height is 3. Again, this is a place where you could put in 3.5, or I'm sorry, you can put in -7 here, but you would have to make this positive, or you can say I'm going to subtract the area of the triangle under the x-axis. Fundamental theorem of calculus. Okay, do that. You take the antiderivative. Evaluate using FTC, fundamental theorem of calculus, from 0 to 5, meaning you take f of 5, capital F of 5, minus f of 0. What did you get? You're like, I don't know, you didn't finish doing the bottom one. This one would be -10. If I did f of 5, 5 squared is 25, minus 25, so -25 plus 15 would be -10. If I substitute in 0, I get 0. Whew. Do you want more? Oh, too bad. There's not another one of these graphs, but we can move on a little bit. Okay, so in here, based on the results of the 5 previous examples, so all the stuff we just did, what inferences can you make about the value of the definite integral and the amount of area bounded by the graph of the integrand of the x-axis? So what that's saying is, what can we say about the value of the definite integral? So that's this thing. So like the integral from a to b of f of x. Remember how I just said these two things match? This was -2x plus 3. The line graph was -2x plus 3. This is going to be equal to the area between f of x and the x-axis from A to B. Okay, so as long as these match, if this is f of x. So if we wanted to find the integral from A to B and have this of f prime instead, we would have to have an f prime graph in order to be able to calculate the area under the curve. Okay, let's do more. And here, find each of the following definite integrals by applying the fundamental theorem of calculus. So remember, fundamental theorem of calculus is the one that I can take the antiderivative and antiderivative, and I can do f of b minus f of a. So if I show your work, this is 2x. I get x squared minus 1/3 x cubed. And I'm going to evaluate from -1 to 2. Make sure that you're doing f of 2 minus f of -1. 2 squared would be 4, minus 2 to the third would be 8/3. -1 squared would be 1, minus, this would be -1/3, and then this is -1 to the third, so there would be negative, so this would be +1/3. Whew, then we do some fractions. This would be the same as if I went 3, this would be 12/3 minus 8/3, which would be 4/3. 1 plus 1/3 would be 4/3. Yeah. Because it'd be, hey, and I get 0. That was a lot of work. Okay, so I jumped into this one, and I was just going to keep jumping into the other ones, but I'm going to actually stop myself. So this one, the reason why it worked is because this function was continuous. Nothing crazy was going on in the graph. But do you notice in like this one, how if I were to graph this at x squared, so when x is equal to 0, I'll put it down here, x cannot equal 0. In the beginning of that really wordy definition, in the part 2 even, if f is continuous function, this one, f is not continuous at x equals 0, which is in this interval from -2 to 3. Therefore, FTC cannot be applied. Anything else that you see would be a problem here? This one also, even though it's at the end point, same thing is true here. X cannot equal 0, therefore f is not continuous. And FTC cannot be applied. Okay, one more. I know you're like, wait, I get to do this with trig too? I do. Find the antiderivative of 2x. Get x squared. This is a continuous function. Cosine and sine curves are all like nice and periodic and stuff. So we get x squared. The antiderivative of cosine is sine of x. I'm still evaluating from 0 to pi. I'm finding f of pi minus f of 0. When you evaluate this one, I'm going to substitute them first, so I get pi squared plus sine of pi. I'm going to just write this down. This one would be 0 squared plus sine of 0. When I think of a sine curve, just so that image is in my head of sine, this would still remain as pi squared. Don't put it in your calculator or anything. I get pi squared sine of pi. If this is 0 to 2 pi, pi is right here, and I would still get 0. Minus, this would be 0. Sine of 0 is 0. Oh man, very boring. And then it says you can check all this with your calculator. Yes, there's a way to do this on your calculator. No, it is not helpful for many, 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 many problems, but to show you how to do this. If you go back to the home screen, and I push math, and, math, and I go down to, instead of n deriv, the next one after it is f integral. You could have just put 9 there too. And then I'm going to type this integral. I'm going to put in this original function, -1 to 2x minus x squared. So I'm writing exactly like it is there. And then a dx. This one, your calculator isn't super helpful. This is -1.5 times 10 to the -14th. What your calculator is doing is calculating the area under the curve, and it's super pixelated. So this number is as close as we can possibly get to 0. So this is a little bit nicer. If you were looking in Y1, or if you have an older calculator like a TI-83 or something, you would have to do it in here. 2x minus x squared. When you put your window, so I'm going to change my window and make sure I've got that interval. So this one says -1 to 2. I want to make sure, so I'm going to make my x min -5, my x max 5. And just so I can see a little bit more, I'm putting -10 to 10. Graph it, I can see a function. Okay, great. And then I want to make this even smaller. Y min, let's do it -5 to 5. Okay, that one looks even prettier. If you do this like this in your calculator, notice I graphed the original function, not this one. I graphed the original function, and I did second calc. Instead of dy dx, which I think you are getting used to, go to number 7, has an integral symbol. And it's going to look like it says lower limit. You can just start typing. So I'm going to type in -1 to 2. Look how pretty it is. And then it gives me the same value. You can see -1.5 times 10 to the -14th, which is just 0. Okay, that's it for today. Thanks so much for listening, for watching, for learning. Ask me questions when you have them. I think you're great. Bye.